Here is something builders get wrong. We keep making the context window bigger and calling it memory. It is not. A fact buried in the middle of a long prompt tends to get recalled far worse than one sitting at the edges. And right now, you are probably stuffing everything into that window and hoping it sticks. So what does memory even mean for an agent? It is not one thing. It is really three separate mechanisms that people blur together. There is the context window, the working memory for the current session. There is retrieval from a large corpus of documents. And there are memory files, the agent's own durable notes. Confuse them, and you build the wrong thing. Here is the map up front. First, the context window. Short-term, working memory, only what the model can attend to right now. Second, retrieval augmented generation, or RAD, long-term memory of a corpus you pointed at. Third, memory files, long-term memory of the agent's own experience and your stated preferences. Three mechanisms, three different jobs. Start with mechanism 1, the context window. This is the live prompt, your conversation so far, the system instructions, the tool outputs. It is the model's working memory, and only what sits inside it can shape the next response. But here is the catch. A new session starts empty. Nothing carries over from the last one unless something outside puts it back. And even within one session, the window is not uniformly reliable. In a paper from 2023 called Lost in the Middle, Liu and colleagues showed a U-shaped curve. Models have been shown to use information best when it sits at the very start or the very end of a long prompt, and their recall drops for facts stranded in the middle. Position matters, not just presence. Why does this happen? As the context grows, the model's attention is spread across more and more tokens, so the signal for any single fact gets thinner. Anthropic calls this context rot. As the window gets larger, accuracy at recalling a specific detail can fall. That is their term for an effect the academic work has documented separately. So the context window has a ceiling, in three ways. It forgets everything between sessions, it gets more expensive as it grows, and it is weakest in the middle, right where a long prompt tends to hide things. Working memory is essential, but it cannot be your only memory. You need something that survives past the current session. That is where mechanism 2 comes in, retrieval augmented generation. RAG gives the model long-term memory of a corpus, a body of documents you choose. The loop is simple. Retrieve the most relevant pieces, augment the prompt with them, then generate the answer. Under the hood, there are three parts: embeddings that turn text into vectors, a vector store to hold them, and a retriever. Here is that pipeline. A query comes in. The retriever compares it against a vector store of embedded documents and pulls back the closest matches. Those top chunks get slotted into the prompt, and the model generates its answer grounded in them. Notice the flow goes one way. Retrieval happens fresh at query time, from a corpus the model never memorized. This is not just theory. Cloud providers ship RAG as a standard pattern. Amazon Web Services describes it as optimizing a model's output, so it references an authoritative knowledge base outside its training data before it answers. That is the whole point. Pull in external, current facts the model was never trained on and ground the response in them. Now, my honest take, and this is where I push back on the hype, more data is not automatically better for RAG. Retrieval is a similarity search. As a corpus grows denser and more self-similar, the retriever starts surfacing chunks that look right but are wrong, and the model answers confidently on the wrong ground. This is a failure mode of naive similarity retrieval, and good chunking, re-ranking, and scoping all soften it. RAG still shines for large, external, well-separated facts. Let me make it concrete for anyone who builds. Picture two functions from two different code bases. They validate input, loop, and return a result, almost identical in shape. To an embedding model, code that looks alike sits very close together. So when you ask about the one you wanted, the retriever can hand back the other, from a completely different project. Code is the hard case, because it is so homogeneous. Mechanism 3 is different in kind. Memory files. These hold the agent's own experience and the preferences you have stated, written to plain files on disk. They survive across sessions, a human can read and edit them, and they are deliberately loaded back in, rather than fished out by similarity. This is recollection of what happened, not a lookup of some outside corpus. Real tools do this today. In Claude Code, Two kinds of memory load each session: a file you write with your instructions, and notes the agent keeps for itself from your corrections. Both live on disk as readable text. The agent records what it learns, then reads it back on demand, so durable facts survive, without holding everything in the window at once. Here is what one actually looks like. A memory file is just readable text. A couple of preference lines: use this package manager, write tests this way. A couple of decision lines: we chose this database, we locked this auth provider. Short, curated, high-value facts. The next session reads this and already knows how you work, with no retrieval step at all. But even durable memory has a budget. In Claude code, only the first 200 lines of the memory index, or the first 25 kilobytes, whichever comes first, load automatically when a session starts. Everything past that waits and loads on demand when it is needed. So even persistent memory is rationed. You still have to decide what earns a place at the top. So what really separates these? The right decision. With RAG, what lives in the index is fixed when you ingest the documents. With memory files, what gets written is increasingly decided by the agent itself, while it works. That is the shift people call agentic memory. The academic map here is a framework from 2023 called COALA, which splits agent memory into working, episodic, semantic, and procedural. Put it together into one clean picture, agent memory splits into short-term and long-term. Short-term is the context window, working memory for right now. Long-term splits again into memory of a corpus, which is RAG, and memory of the agent's own experience, which is memory files. 3 mechanisms, 2 time horizons, 1 map to reason from. 2 more mechanisms keep the window lean. Context editing clears out old tool results you no longer need. Compaction summarizes the conversation as it nears the limit. Together they shrink active context, while memory files preserve what must outlive the summary. Anthropic reports that pairing memory with context editing improved one internal agentic search evaluation by about 39% and cut token use by about 84% on a 100-turn web search test. These are Anthropic's own internal measurements, so treat them as directional. Here is the guardrail. When each one is the wrong tool, do not trust the context window to hold facts that must survive across sessions, because it starts empty every time. Be careful using RAG for your agent's own decisions, or for small, homogeneous data like code, where similarity retrieval misfires. And do not reach for memory files to hold a huge, fast-changing corpus. That is exactly what RAG is for. So, the architect's lens. 3 takeaways. 1. There are 3 kinds of memory: working, corpus, and experience, and they are not interchangeable. 2. Match the mechanism to the data. RAG is for large external facts, not for your own code or decisions, and more data is not automatically better. 3. The frontier is the right decision. Let the agent curate durable memory and keep active context lean with compaction and editing. If this helped you build better, subscribe, and I will see you in the next one.